in this lecture, we will solve a couple of problems in heat exchangers. Example number 1. In a parallel flow double pipe heat exchanger, water flows through the inner pipe and is heated from 20 to 70. Oil flowing through the annulus is cooled from 200 degrees centigrade to 100 degrees centigrade. So let's say we have got a double pipe heat exchanger, which is, so I have got an outer pipe. Let's say I have got an outer pipe. So through the outer pipe, we have got oil. That is, say it's a parallel flow. Let's say this is the inlet over here for the outer pipe. And so you have, so this is the hot fluid. So the inlet temperature of the hot fluid is going to be 200. So THI, that is 200 degrees centigrade. And THO, that is the exit temperature of the hot fluid, that is 100 degrees centigrade. And we have water that is flowing through the inner tube. So let me represent it with another color. So let's say this is my inner pipe. And here water flows through the inner pipe. And since it is parallel flow, we have the inlet and the exit for both the fluids on the same sides. So TCI is going to be 20 degrees centigrade. That is the temperature of the hot fluid at the inlet, and temperature of, cold fluid at the inlet, and cold fluid at the exit, it is going to be 70 degrees centigrade. Okay. So obviously, so if you look at a parallel flow heat exchanger, in a generally, okay, say this is your inlet and exit. Okay. So when you have the hot fluid loses heat. So it moves from THI to THO. And your cold fluid gains heat. So it moves from TCI to TCO. And the direction is the same. So in the increasing X direction, you have got both the fluids flowing in the same direction towards the right. Okay. So this is how a parallel flow heat exchanger works. So now the question is, determine the minimum temperature to which the oil may be cooled. Okay. So what is the minimum temperature to which it can be cooled? So your hot fluid and the cold fluid, if you look at this particular picture, THO is not equal to TCO, which means the equilibrium is not attained between these two fluids. Okay. And there is a possibility that an equilibrium temperature can be attained. And that is what is being asked in this particular question. What is the minimum temperature to which the oil may be cooled? Or the question can also be the other way around. What is the maximum temperature to which the water can be heated? Which means both of them attain a temperature, let's say T. So this is, or let's say TF, the final temperature, where you get equilibrium between the hot fluid and the cold fluid temperatures. Okay. So now to get this particular value TF, because the temperatures of the cold fluid and the hot fluid only is given, so we need to find out what is this value of temperature TF. So to start with, we can say m dot h CPH THI minus THO, because the inlet temperature of the hot fluid is greater than the exit temperature of the hot fluid. M dot C times CPC times TCO minus TCI. This is simple energy balance. Okay. And what we know is m dot h CPH, this value is unknown. THI minus THO is going to be 200 minus 100. And here we have got m dot C CPC times 70 minus 20. So this is 100 times m dot h CPH is equal to 50 times m dot c CPC. Okay, and so now what I can do is I can get a ratio like m dot c CPC divided by m dot h CPH. This is going to be equal to 100 divided by 50, which gives me 2. Okay, now the question is to find out the value of this equilibrium temperature. So we can write m dot h CPH THI minus TF, because that is the maximum or the minimum temperature to which the hot fluid can be cooled. That is equal to m dot c CPC times TF minus TCI, because this is the maximum temperature which the hot fluid can be, sorry, cold fluid can be heated up. Okay. So now what we know is m dot c by m dot h, that is the capacitance rate, capital CC by capital CH. That is going to be 2. So we can write this as THI minus TF is equal to m dot c CPC divided by m dot h CPH times TF minus TCI. And that is simply 2 times TF minus TCI. And so if we expand this particular simple energy balance equation, we would get THI minus TF is equal to 2TF minus 2TCI. So if we rearrange the equation, that would be 3TF times 3TF, that is going to be equal to THI plus 2 times TCI. And THI happens to be 200. And TCI, I think it's 20 or 30. How much is that? So 20. So 2 times 20. So that gives us 240. And so TF is going to be 240 divided by 3, which gives us 80 degrees centigrade. So this is the minimum temperature to which your hot fluid can be cooled and the maximum temperature to which the cold fluid can be heated up. Okay, so that is our first question over here. Then let's move on to the second example. The flow rates of hot and cold water streams running through a parallel flow heat exchanger are 0.2 and 0.5 kilogram per second respectively. Inlet temperatures are given. The exit temperature of the hot water is given. If the individual heat transfer coefficient on both sides, that is for the inner tube and the outer tube, that is 650 watt per meter squared Kelvin, calculate the area of heat transfer. So if you look at the given details, so the mass flow rate of the hot fluid, so m dot h is 0.2 kilogram per second. M dot c is 0.5 kilogram per second. Cp for water. So in both the cases, Cp, C and Cph, that is 4180 joule per kilogram Kelvin. Or to be exact, we can say 4187. That is what we normally use, 4187 joule per kilogram Kelvin. The inlet temperature of the hot fluid is 75. The inlet temperature of the cold fluid is 20. And the exit temperature of the hot fluid is 45. And they have given the heat transfer coefficient on both sides, Hi and Ho. For the inner pipe and the outer pipe, that is 650 watt per meter squared Kelvin. Okay. And now what they want us to find out is what is the area of this heat transfer. Okay. So once again, this heat exchanger is a parallel flow heat exchanger. Okay. So the general equation is going to be Q equal to U times A delta T Lm. So delta TLM is your logarithmic mean temperature difference. Here, three temperatures are known. So we can also find out the value of TCO by simply applying the energy balance equation. So M dot H, CPH, THI minus THO, that is going to be equal to M dot C times CPC, TCO minus TCI. Okay, so this guy is 0.2 and CPH and CPC are same on both sides. So this can be cancelled out. You can cancel it out every single time because uh, both the fluids are supposed to be water. We are cancelling it out over here. So 0.2 times 75 minus 45 is going to be equal to 0.5 times TCO minus 20. Okay, so this guy over here would be 0.2 times 30, and this is 0.5 TCO minus 0.5 minus 20 into 0.5 would be 10. So 0.2 into 30 would be 6. So 0.5 TCO is going to be 6 plus 10, 16. So TCO is going to be equal to 32 degrees centigrade. Okay. I guess that should be the answer that we have. Yeah, TCO is 32. So now we can get the value of this logarithmic mean temperature difference. So logarithmic mean temperature difference, delta TLM, can be written as theta 1 minus theta 2 divided by ln of theta 1 by theta 2. So that is going to be THI minus TCI minus THO minus TCO whole divided by ln of THI minus TCI divided by THO minus TCO. Okay, so if you substitute the values over here, so that is going to be 75 minus 20 minus 45 minus 32 whole divided by ln of 75 minus 20 divided by 45 minus 32. So that should give you delta T LM according to the book is 29.12 degrees centigrade, or you can also call this as 29.12 Kelvin. Remember, this is temperature difference. So the moment you find the word temperature difference, it's going to be the same in degree centigrade, Kelvin, Fahrenheit, whatever it is. Okay, so please do not add plus 273 to it. You will end up getting a wrong answer over here if you add 273 to it. Okay, so now we have got delta TLM. And so if you look at this equation, Q equal to UA delta TLM, now delta TLM is known. Q can be found out. Q is equal to M dot H CPH THI minus THO. You can also use M dot C CPC TCO minus TCI. Both should give you the same answer. So 0.2 times 4187 multiplied by 75 minus 45. So this should give you the answer in watts or kilowatts. So the book answer is 25.122 kilowatts, or let's say 25.12 kilowatts. And by the way, I'm using the problems from Heat and Mass Transfer by Rajput. Okay, so that is the reference that I'm looking at. The next one is going to be U, the overall heat transfer coefficient. So 1 by U is going to be equal to 1 by HI plus 1 by HO. So that is 1 by 625, or sorry, 650 plus 1 by 650. So that is 2 by 650. So U is going to be equal to 650 divided by 2, which is 325 watt per meter squared Kelvin. And therefore, now we know that, so the general equation is Q is equal to UA delta T Lm. The question is, we are supposed to find out the area of heat transfer. So Q divided by U times delta T Lm. So now Q happens to be 25.12 into 10 to the power 3 divided by 325 multiplied by delta TLM, that is 29.12. So we get the final answer for area, which happens to be 2.66 meters squared. So that is the area of heat transfer for this particular heat exchanger. So for heat transfer rate, you have got three equations. It's very simple. So either you can use Q is equal to UA delta T Lm, or you can use Q is equal to M dot H CPH THI minus THO, or you can use M dot C CPC TCO minus TCI. So these are the basic equations that we have used in solving the problem. And for any problem in heat transfer, these equations are going to be the fundamental equations. Okay. So now let's look at problem number 3. The problem number 3 is almost same as that of your problem number 2. Once again, it refers to a parallel flow heat exchanger here. So heat transferred per hour. So Q is given to you directly. So Q is given inside heat transfer coefficient. So that is going to be HI. This is HI. Outside heat transfer coefficient is HO. The inlet and outlet temperature. So this is going to be THI. 450 is THI. 250 is THO. TCI is 60 and TCO is 120. And the diameters are given. So inside diameter, so DI is 50 mm and DO is 60 mm, which means RI is going to be 25 mm or 0.025 meters. And RO is going to be 30 mm, which is going to be 0.03 meters. Okay. The question is to calculate the length of the tube required. So once again, the general expression is going to be Q is equal to UA times delta TLM. Okay. So all the four temperatures are known, so you can calculate delta TLM straight away. U can be found out because HI is given, HO is given, additionally the radii are given. So using this, you will be able to get the value of overall heat transfer coefficient. Q can be found out because you need not find out. The value is given straight away, 155,450 kilojoule. So that is given straight away. So this area, this is nothing but pi times dl. That is the circumferential area of the tube. So that is going to be pi dl. So d is going to be your the outer diameter of the tube. Okay. And so you will be able to calculate the value of L. So now let's calculate delta TLM again. So that is going to be THI minus TCI minus THO minus TCO whole divided by ln of THI minus TCI whole divided by THO minus TCO. So if you substitute the values over here, so this is going to be 450 minus 60 minus 250 minus 120 whole divided by ln of 450 minus 60 divided by 250 minus 120. So on calculating, you will be getting a value in degree centigrade. So let's see what value is given in your textbook, which is 236.66. That is the logarithmic mean temperature difference over here. Now, additionally, so Q is known. The next thing that we are supposed to find out is U. So it is for this, I took this particular problem. So 1 by U, that is going to be equal to R naught by Ri into 1 by Hi plus 1 by Ho. Okay, so this is what you should be aware of. So when the radii or the diameter is given, make sure that that is taken into account. We have done this in convective heat transfer. So this is the convective resistance on the inside on the inside of the tube, and this is the convective resistance on the annulus or outside the inner tube. Okay, so this is going to be equal to 0.03 divided by 0.025 multiplied by 1 by hi is 120 plus 1 by 195. So you would be getting a numerical value. So for 1 by u, so get that value and invert it. So u is going to be equal to 1 by all this. So that should give you the answer in watt per meter squared Kelvin. And according to your textbook, this is 66.09 watt per meter squared Kelvin. Okay. So now the final equation is going to be equal to Q is equal to U times pi D naught times L into your delta T L. So Q is given. That was equal to 155,450. U is 66.09. The outer diameter is 0.06, isn't it? 0.06. L is what we are supposed to find out, multiplied by 236.66. So now if you rearrange this equation and solve it in your calculator, you should be getting the final value of length of the heat exchanger, which according to your textbook is 14.65 meters. Okay. And we'll look at one more example and then close this lecture. In a certain double pipe heat exchanger, water flows and gets cooled from 95 to 65 at the same time. The same mass flow rate of cooling water enters the heat exchanger. The flow conditions are such that the overall heat transfer coefficient remains constant at 2270 watt per meter squared Kelvin. So what is given is for both the fluids, m dot C and m dot H, it is common, which is 5,000 kilogram per hour. So the hard fluid happens to be water. So for water, what we know is that's going to be equal to 4187. But in this particular problem, they are asking us to consider, assume for both streams Cp is going to be equal to 4,200 joule per kilogram Kelvin. So that makes our job simple. Cpc equal to Cph is 4,200 joule per kilogram Kelvin. Okay. And they have said the entry temperature of the hot fluid is 95. Exit temperature of the hot fluid is 65. Entry temperature of the cold fluid is 30. Overall heat transfer coefficient is given as 2270 watt per meter squared Kelvin. And what is that they want us to find out? The heat transfer area that is required. What is the value of the heat transfer area? The second one is they are asking us to find out the value of effectiveness. Area we have already done. So that is going to be equal to Q equal to UA times delta TL. So you would be using m dot H CPH THI minus THO. That is going to be equal to m dot C CPC times TCO minus TCI. Okay. And in this case, m dot H is same as m dot C. CPH is same as CPC. That makes our job very easy. So this is going to be 95 minus 65. That is going to be equal to TCO minus 30. So this guy over here is 30. So TCO minus 30. So TCO is going to be equal to 60 degrees centigrade. Okay. So if you want to find out Q, so Q is going to be equal to, let's say, m dot H CPH THI minus THO. So that is going to be equal to 5,000 kilogram per hour. So let's convert it to kilogram per second. So divided by 3,600 into 4,200 into 95 minus 65, which is going to be 30. So this should give you the value of Q in watts or kilowatts. So according to the textbook, the value for this is, they have not given this explicitly, And I'll tell you the reason and you will be able to find out in a short while. Okay, so this is going to be your Q. Okay, or you can calculate it. Let me use a calculator over here. So 5,000 divided by 3,600 multiplied by 4,200 into 30. So that is 175 kilowatts. Okay, so now delta TLM, we can find out. It's a parallel flow heat exchanger again. So THI minus TCI minus THO minus TCO whole divided by ln of THI minus TCI divided by THO minus TCO. So that is going to be equal to 95 minus 30 minus 65 minus 60 whole divided by ln of 95 minus 30 divided by 65 minus 60. So this should give you the value of the logarithmic mean temperature difference over here. So this is same as what we have done already. So this is 23.4 degrees centigrade according to the answer from your textbook. So overall heat transfer coefficient was given straight away. So A is going to be equal to Q divided by U times delta T Lm. Q is 175 into 10 to the power 3 divided by your overall heat transfer coefficient was 2270 multiplied by 23.4. So this is going to be equal to 32.95 meters squared according to your textbook. Okay. This we have already done and you should be familiar with the procedure by now. The second part is effectiveness. So the definition of effectiveness is going to be equal to Q actual divided by Q maximum. So the definition is what is the actual heat transfer to the maximum possible heat transfer. So that is going to be your effectiveness. So the actual heat transfer, in this case, you can take it as in a real case scenario, say when you're running an experiment in a lab, we always ask or it is generally specified that you always take the heat that is gained by the cold fluid. In the examples that we solve, we assume that the energy is balanced, which means QH is going to be equal to QC. So you can take any one of them. But in a real case scenario, it is always the heat that is gained by the cold fluid. So in this case, it could be either m dot h CPH THI minus THO or m dot C CPC TCO minus TCI. Okay. So in this particular scenario, this maximum possible heat transfer can be either written as m dot h CPH or m dot C CPC because both of them are same. M dot H is equal to m dot C and CPH is equal to CPC. So you can take any one of these and the maximum possible heat transfer is going to be THI minus TCI. So this gets cancelled. And so your THI minus THO, that is going to be equal to 95 minus 65 divided by 95 minus 30. So 30 divided by 65. So that is going to be equal to 0.461. Okay. So in this particular case, your m dot h CPH is equal to m dot C CPC. What if both of them are different? So in that scenario, the general equation actually happens to be your effectiveness is generally defined as, so your this is this could be your anything, your QH or QC divided by Q max. So let's take QH. So that is going to be m dot h CPH, okay, divided by capital C minimum. So this is going to be THI minus THO. And here, this is going to be THI minus TCI. So the denominator is supposed to be the minimum capacitance rate. So in a question involving this, always check m dot h CPH and m dot C CPC. Of these, which one is minimum? Take that and substitute it over here. So the minimum of these two values is supposed to be taken and substituted in this particular equation. Okay, we'll meet you in the next video. Thank you.